Hey there, ready to unlock some serious machine learning speed. Today we're diving into light GBM. It's an algorithm that claims to turbocharge one of the most popular prediction methods out there. You know, gradient boosting decision trees?
Right.
You already know GBDT is a powerhouse, but it can get bogged down when dealing with massive data sets.
Yeah.
And that's where light GBM comes in. It promises to speed things up by up to 20 times.
Wow.
We're going to unpack this fascinating research paper from the 2017 Neural Information Processing Systems Conference. And I've got just the person to help us break it all down.
What's exciting here is that light GBM isn't just about brute force speed. It introduces some really elegant techniques to make the training process more efficient without sacrificing accuracy.
Okay, I'm intrigued. So let's get into the specifics. The paper highlights two key innovations: gradient-based one-side sampling, GOSS, and exclusive feature bundling, EFB. Can you walk us through how those work?
Let's start with GOSS. Imagine you're training a model to predict whether someone will click on an ad. You have tons of data points, each representing a person and their characteristics. GOSS focuses on the data points where the model is making the biggest errors, the ones where it needs the most training. It keeps all of these high error points and then takes a smaller sample from the data points where the model is already doing pretty well.
So it's kind of like a teacher focusing their attention on the students who are struggling the most while still keeping the rest of the class engaged.
Exactly. And this targeted sampling strategy allows GOSS to make much faster progress during training without losing sight of the overall picture.
That makes a lot of sense. And what about EFB? What's the clever trick there?
Think of EFB like this. You're packing for a trip and you want to fit as much as possible into your suitcase. You wouldn't just throw everything in randomly, right? You'd group similar items together, roll up your clothes, and use packing cubes to make the most of the space.
Okay, I'm a master packer, so I totally get that.
Well, EFB does something similar with data. It looks for features that rarely appear together, meaning they rarely both have a value other than 0. And then it cleverly bundles these features together, reducing the total number of features the algorithm has to consider.
So it's like creating a more compact representation of the data without losing any essential information.
Precisely. And this not only speeds up calculations, but also reduces memory usage, which is a big deal when you're dealing with massive data sets.
All right, so we've got these two clever tricks, GOSS and EFB working together to streamline the training process. But did they actually deliver on that promise of a 20x speed boost?
The researchers tested light GBM on 5 different real-world data sets, some with tons of features, some with sparse data, some with dense data, a good mix to really put it through its paces, and the results were impressive.
I'm on the edge of my seat here.
They saw speedups ranging from 6 times faster all the way up to 21 times faster compared to existing methods. And the key here is that this speed boost didn't come at the expense of accuracy. Light GBM's predictions were just as good as the slower methods.
That's seriously impressive. So we're talking about real potential for practical applications here, not just an academic exercise.
Absolutely. Light GBM has the potential to change how we approach all sorts of machine learning tasks, especially when dealing with huge data sets.
But before we get too carried away with the applications, I want to go back to GOSS for a second. You mentioned that it focuses on the data points where the model is making the biggest errors. How does it actually figure out which points those are? I mean, it can't know the correct answer beforehand, right?
That's a great question, and it gets to the heart of how GOSS works. It all comes down to something called gradients.
Okay, gradients. That rings a bell from calculus class, but refresh my memory on what they represent in this context.
In machine learning, gradients essentially tell us how much the model needs to adjust its predictions to improve its accuracy. A large gradient for a particular data point means the model's current prediction for that point is way off the mark.
So it's like a measure of the model's confidence in its predictor for each data point.
That's a good way to think about it. And GOSS cleverly exploits these gradients to guide its sampling strategy.
I see where you're going with this. So instead of blindly sampling data points, GOSS prioritizes the ones with the largest gradients, because those are the ones that will have the biggest impact on improving the model's overall performance.
You got it. It's about making the most of each training iteration.
All right, that clears things up a lot.
Yeah.
Now let's delve a bit deeper into EFB. How does it actually go about bundling those features together? Is it just randomly grouping things, or is there a more sophisticated method at play?
It's not random at all. EFB uses a clever approach based on graph theory. Imagine each feature as a point on a graph, and we draw lines connecting features that frequently have non-zero values together.
Okay, I'm visualizing a network of features with lines showing which ones tend to hang out together in the data.
Exactly. Now, the features that are rarely connected, the ones that don't often have non-zero values at the same time, those are the ones that EFB targets for bundling. It's like finding those independent, solitary features that don't overlap much with others.
So it's not just about bundling any two random features. It's about strategically grouping those that are already independent in the data. I like that. It seems like a very natural way to reduce the feature space without losing information. But how does it actually combine them?
EFB uses a technique called offsetting. Let's say we have two features, age and income, that we want to bundle. EFB might add a constant value, say 100, to all the income values.
So instead of income ranging from 0 to 100,000, it would now range from 100 to 100,100.
Precisely. And this offset ensures that the values from age and the shifted income never overlap. Even though they're bundled together, we can still perfectly distinguish between them.
That's clever. It's like assigning each feature its own unique zone within the bundled feature so there's no mixing or confusion. This whole approach to feature bundling seems very elegant. But is there a downside? Is there ever a situation where EFB might not be the best choice?
That's a great question. And it highlights the importance of understanding the nuances of these techniques. EFB is particularly powerful for datasets with sparse features where many features are 0 most of the time. But if you have a dataset where most features have non-zero values for most data points, EFB might not provide as much benefit.
So it's not a one-size-fits-all solution, but rather a tool that's particularly well-suited for certain types of datasets.
Exactly, and that's why it's so important to understand not just what these techniques do, but also when and why they're effective.
It's about knowing the right tool for the job. So we've covered the how of like GBM, but I want to shift gears a bit and talk about the so what. What kind of real-world impact is this algorithm having? The paper mentions click prediction and ranking, but I'm guessing its applications go far beyond that.
You're absolutely right. Light GBM is being used in a wide range of fields, from finance and healthcare to environmental science and even online marketing.
Okay, color me intrigued. Give me some specifics. How is it being used in these different areas?
Let's start with finance. Light GBM is incredibly effective at detecting fraudulent transactions. It can analyze patterns in financial data to identify anomalies that might indicate fraudulent activity.
So it's like having a superpowered fraud detective working behind the scenes to protect our bank accounts.
Exactly. And in healthcare, Light GBM is being used to develop predictive models that can help doctors diagnose diseases earlier and more accurately. It can analyze patient data like medical history and lab results to identify patterns that might suggest a particular condition.
Wow, so it's not just catching bad guys, it's potentially saving lives.
Mm-hmm.
Are there any limitations to its use in a field as sensitive as healthcare?
Of course, as with any powerful tool, careful consideration and validation are crucial. The accuracy and reliability of any model depend heavily on the quality and representativeness of the data it's trained on.
That makes sense. You can't just throw any data at it and expect perfect predictions.
Mm-hmm.
So what about environmental science? You mentioned it's being used there as well.
Yes, Light GBM is proving very useful in analyzing massive data sets of satellite imagery and sensor data to track things like deforestation, monitor changes in ecosystems, and predict the impacts of climate change. It's like having a watchful eye on the planet, helping us understand and address environmental challenges.
That's incredible. It seems like Light GBM is becoming a go-to tool for any field that deals with large, complex data sets.
It's certainly gaining popularity, and for good reason. Its efficiency and scalability make it a powerful tool for tackling a wide range of data-driven challenges.
Okay, last question before we move on. You've painted a very positive picture of Light GBM, and its benefits are clear. But I'm wondering, is there anything about this algorithm that might raise concerns? Any potential downsides we should be aware of?
That's a very important question. While Light GBM itself isn't inherently problematic, the way it's used, like any algorithm, can have implications. One thing to consider is the potential for unintended consequences.
Do you give me an example?
Imagine using Light GBM to personalize content recommendations. It might be very effective at showing users what they want to see, but it could also lead to filter bubbles where people are only exposed to information that confirms their existing beliefs.
No, it's a great point. It's like being stuck in an echo chamber, missing out on diverse perspectives and critical thinking.
Exactly. So while Light GBM can be incredibly powerful for tasks like content personalization, it's important to be aware of the potential downsides and use it responsibly.
So it's not just about the technical capabilities of the algorithm. It's also about the human element, the choices we make and how we apply it. Are there any other potential concerns we should be aware of?
Another important consideration is the interpretability of the model. Light GBM, like many machine learning models, can be a bit of a black box. It can make accurate predictions, but it's not always easy to understand why it makes those predictions.
So we might know what it's predicting, but not necessarily how it arrived at that prediction. Why is that a concern?
It becomes crucial in situations where understanding the reasoning behind a decision is essential. For example, if a bank uses light GBM to approve or deny loans, it's important to be able to explain the factors that went into that decision, both for regulatory reasons and for fairness.
That makes sense. We don't want algorithms making life-altering decisions without any transparency or accountability. So are there ways to address this black box problem?
Yes. There's a growing field of research focused on making machine learning models more interpretable and explainable. There are techniques that can help us understand which features are most influential in a model's predictions and how those features interact.
So it's like shining a light into the black box, giving us a glimpse of the decision-making process.
Exactly, and this interpretability is crucial for building trust in machine learning models and ensuring that they're used ethically and responsibly.
It sounds like there's a lot of ongoing work to make these powerful algorithms more transparent and accountable.
Absolutely. As machine learning becomes increasingly integrated into our lives, it's essential to prioritize transparency and understand the societal impacts of these technologies.
Well, this has been a fascinating deep dive into the world of light GBM. We've learned how its clever techniques, GOSS and EFB, make it a speed demon when it comes to training machine learning models. And we've explored its wide-ranging applications, from fraud detection to environmental monitoring.
It's a testament to how innovation in algorithm design can have a ripple effect across multiple domains, accelerating progress and helping us tackle complex problems.
And we've also touched on the importance of considering the ethical implications,
Yeah.
ensuring that these powerful tools are used responsibly and transparently.
Because ultimately, technology is a means to an end. It's up to us to guide its development and application in a way that benefits humanity.
This deep dive has certainly given me a lot to think about. It's inspiring to see how algorithms like light GBM are pushing the boundaries of what's possible, and it's equally important to engage in thoughtful discussions about their responsible use.
Absolutely. As we continue to explore the frontiers of artificial intelligence, it's crucial to approach these advancements with both enthusiasm and critical thinking.
Well said. To our listeners out there, we encourage you to keep learning, keep questioning, and keep exploring the fascinating world of machine learning. Who knows what groundbreaking discoveries await us just around the corner?
And maybe, just maybe, you'll be the one to develop the next light GBM, an algorithm that not only pushes the boundaries of speed and efficiency, but also helps us build a more equitable and sustainable future.
Thanks for joining us on this deep dive. Until next time, stay curious.